Peter Hill Explains, where I invite you to join the science teaching conversation with me about how we perceive colour, or the more technical term, the way the perception is mapped, is called chromacity, where chroma means for colour, the Latin for colour is chrome, and chromacity. So I'm going to talk about that at the moment. Just a bit before I start off, I'm now sort of been able to actually record, put the USB in and publish, and should be able to. I've got it going up to YouTube, and I'm looking at how you get it onto Facebook and various things like that. But as you go on, there's also a need to actually indicate whether these are expert podcasts or school grade podcasts. We are describing things. So I'll get icon buttons to at least go on the YouTubes to tell you whether it's a podcast ahead where I'm walking, driving, or doing various activities, and the level, whether it's a expert teacher level podcast or it's an introductory podcast. I don't know. I'll have to do the podcast first and make a decision about it afterwards. This is actually done sitting out here in a little bit of bushland and a bit of quiet, and as I try to get it done. So colour, I suppose. First thing is, some people are colourblind, other people can see a full range of colours, and people go Roy G. Biv, red, orange, yellow, green, blue, indigo, violet are the different colours here. We are obviously somehow, when we see something happens inside our eye to give a signal to our brain that that particular thing at that location is of a certain colour. So we're going to go into that and look at something called a chromacity map or graph, and try and undo that, because it's certain lines about it. So that graph is like a table of all possible colours you can see, and there's certain lines on it which are for lasers and spectroscope, and there's another line for heating something up. There's these unique lines that you look at, and there's lots of tricks to it. You can see pseudo colours that you could never see before. There's tricks that you can see to look at it. So what happens is the light is generated outside and enters our eyes through a lens and hits the back of our eye on a retina, and the retina is full of photosensitive. That means it detects light detecting cells. You've got little dyes on it, dye molecules, and when the light hits that, they become conductive or release ions and activate nerve pulses. Those pulses undergo a fair amount of processing in the back of the eye and actually come out, and we put high density colour vision in the macula in the centre of your eye and on the outside of the eye. A larger area, low resolution, low light sensitivity cells called rod cells, and they're put to sleep with something called visual purple. So when the light level is up, the light level is detected. There's actually more than retinal cells. There's other light detecting cells which actually just tell the brain there's light. So you can actually lose your vision, but the light can affect your circadian rhythm. So there's another group of cells which go into the back of your brain, besides the rod and cone cells. The rod cells are around the outside of your peripheral vision, on the outside of your cell, and when a chemical is given by your eye called visual purple, it goes out, it wakes up the cone cells, the rod cells put the cone cells to sleep. You lose your colour vision and you get black and white night vision, and that's peripheral vision. So in general, you can see movement out of the side of your eye. If it's in the central vision, you can't see movement as well, and your night vision is better out of the side of your eye. So your peripheral vision is better for night vision, and you'll know that if you ever have to do security guard work at night or things like that. You don't want a big flashlight going around the place. You want to walk around at night in the dark, and there's a certain way that you learn to look at objects through the side of your eyes to get your night vision and movement, and you've also got to protect your night vision. So when you have a bright light, the visual purple catalyzes. There's an enzyme which eats it up, and you have to actually develop your night vision. But we're not talking about that. I'm just giving that as general background, just data dumping as it comes. I want to look at the cone cells. So cone cells they point up cells, and they're pointing towards the light, and as the light hits the cone cells, it generates signals. And the way that you see different colours is that you have a combination of 3 grades of cone cells, and each cone cell can pretty well see the entire light spectrum, but their dye that's in them is optimized for different wavelength ranges. And what has happened is that us mammals have lost our 3-colour vision, as we used to be many years ago. Before, with the dinosaurs, we were only out at night. Colour vision wasn't useful, and we have, and most mammals have 2-colour vision, and very good night vision. But other animals, which weren't related to mammals, like the I suppose turtles was one example. Turtles are very fascinating, but birds, I think pigeons can see 5, ducks can see 4 different grades of colour. They've evolved in a different way. And humans, who are great apes, because we had a need for it to actually see colour vision, to see ripe fruit is the idea. We developed the colour vision that we have at the moment as a mutation. So one of our cells mutated back, we evolved back, we devolved and evolved back to have different levels of vision. So there's 3 different spectra, and we're going into that idea. So a spectra actually comes from spectroscopy, from the divining of colours from a light source, and it really means ghost hunting. A spectre, the spectre of something is a ghostly colour, and so the light broken up through a prism was considered to be a ghost of light, a spectrum. And so in the Middle Ages you had spectroscopists. They were the original Ghostbusters, but people began to hang on and look at that spectrum, and we'll hang on to that idea a little bit more. You have a spectrum which is your typical rainbow, and it depends on how the dispersion, whether it's negative or positive dispersion into your prism, whether you actually get a what shape of prism light you get. But in general, the blue light gets bent more because that's closer to an absorption line within the glass, so it gets bent more. So blue's at the bottom, red's at the top, and a spectrum is a distribution of light of pure single wavelength. So I get a complex colour, I put it through a prism, and I will get a spectrum which is an intensity of light. And when you look at it, you'll see dim and light, dim and bright bands, and we convert that into a graph, a 2-dimensional graph, where we have a light detector and it moves across, and as it increases, the graph increases. So we get a graph of, on the bottom axis, the x-axis is wavelength, on the vertical axis is intensity. With that, sorry, just going that into my head. So that is a spectrum. So a spectrum, a physical spectrum, when you pick it, is sort of a rainbow with bands in it. You can often, you can see it through diffraction gratings, prisms off CDs if you hold it there, and then the spectra, which we say, well, the spectra, or that coloured rainbow represents a graph. So there's so much, it starts off with so much red, and so much yellow, green and blue, and across. Now, your eyes are a pretty sophisticated but blunt instrument to do spectra. They're nothing compared to a machine's spectroscopy. So a machine can see an unbelievable number of colours. Now, what I mean by colours is that your eyes has only 3 bins, detection bins, and the detection bins cover a large amount of it, a large amount. So, just for saying that we're going to have red 0 and violet or violet 9 and ultraviolet 10. This is, I'm only saying that so I can actually create a graph in your head, a podcast graph in your head, and say your red cone will absorb strongly, building up from 0 to 3, leveling off, dropping down by 5, and then going right down by 7. And there's a trick in there just before we go too far. So I'm actually drawing a graph of your red cone absorbing in the red, the low numbers. Your green cone is absorbing in the middle range. It's pretty much the same, it's only slightly different, and the blue cone is distinctly across into the blue area. So you've got 3 different cones, and for any light coming in, you get 3 numbers, and basically your TV, any pictures that we send across there, your JPEG or anything, each pixel is given 3 numbers to make it up to say, well, there's a picture, and I'm going to simulate that with what I've got, a computer giving the same levels of psychological pictures. Now, the actual, so essentially, computers only produce one sort of 3-dimensional combination of light, and you only see one 3-dimensional combination of light, but in actual fact, you can actually have two molecules. They look the same color, but in fact they've got vastly different spectrum. So an example would be, say, if its spectrum goes from 0 to 10, there's one which is at it's got emission in the even, so that's for the 0 bin, the 2 bin, the 3 bin, the 4 bin, the 5 bin, the 6. I say that 3. The 0 bin, the 2 bin, the 4 bin, the 6 bin, the 8 bin, and the 10 bin. Whereas you've got some other molecule which doesn't have a broad thing. It's also similarly shaped, and that's goes in the 1, 3. You've got peaks. Molecules which are peak in those areas. Now, visually, they'll look very much the same, but if you have laser light which actually illuminates odd and laser light illuminates even, you can have something, and its color will suddenly vanish. So there's all this stuff in the colouring of light, and so what happens is that you have a lamp which is projecting a colour. So what you see, so different lamp spectra, different light spectra on the complicated. So you have a complicated light source, a complicated object, and you simplify it, and so you can actually change your perceived colour by your different lamps. So if you have a mercury lamp as to a hydrogen lamp, the colouring will look completely different through it, although few people know it. So you can have a colour filter in front of your face, and it will look completely different, or you can have a colour filter in front of your lamp. And so at the moment you have no colour filter, and you judge 2 colours to be the same. And just to put this in perspective, say for a duck, ducks have pretty good green spotters, and what they do is they have a much more nuanced sense of green. And so for us, 2 things will look for the green, but it will be able to say there's water there. They can actually spot water. And so a lot of birds, insects, butterflies, for instance, I think butterflies have 5 degrees of colour. So let's go into it. So the big main thing is that we perceive in a very simple way, and then we get our machines to go, all right, we're not going to put more than 4 colour sensors in. We're going to have the same number of colour sensors as the human eye, and we're going to record the same stimulus as we would receive from it. So try and match the human eye as much as possible. So when I take a photo with a machine, I print something out and I hold it up, and they look identical to the 2. But like if you had a picture which looks normal in normal light and hold it up to the actual object, in sunlight the picture would look the same, but in if you illuminated both with these spectral lamps, the spectral lamp could actually wipe out the object, but you'd still see the picture. So if you can get your mind around that. So this is sort of all the interest to it, and I know that I work So, like I live and work in a world which is all two-dimensional. A picture's a picture, that's it, that's all over. And of course this is highly intensively interesting for building camouflage, so you can actually produce a searchlight which you have your enemies camouflage, and you can produce a searchlight which makes them stand out like anything. It's a pretty amazing thing that you can do, and so there's more to it. So what I want to do is talk about this psychological map called not a chromograph, a chromograph map, whether that's them, and it's a three-dimensional picture, because you've got three cone cells covering three different areas, and on the X is the red, on the Y is the green, and on the Z is the blue. And for anything that you see, it will illuminate a little spot in that three-dimensional graph. So in your eyes there. Now, certain things that we can do. That's a three-dimensional graph. A three-dimensional graph is pretty difficult to hold in a book, and so we sort of can subtract and add dimensions in a pretty natty way, and it's pretty interesting that the first person who unstuck what colour was, which is Maxwell, I end up doing something very similar to this. And so, say we've got this graph, and anything you see, any picture you see will populate as a cloud of different colours. For each pixel will be a different colour and different intensity. Things at low intensity will be all the way down, and so if you have something at 111, it'll be dim, and if you have something which is the same colour but brighter, that will be at, say, 444. It'll be there. So a line going out from the axis is a particular colour, as perceived colour. So it's actually colours are turned into angles, but that's not so helpful for us. So we have two colours, a dim colour and a bright colour. And what we do is we say, for this graph, we're only going to consider colours of the same brightness. And that is that they stimulate the cones equally. Okay, and there's a mathematical way that they do it. So if I've got a dim green, what I do is I increase it till it's got the same maximal power. And so if I add the signal from all three cones, they add up to 100%. So I say a particular colour I'm looking at, I'm going to increase its intensity, so it's at 20% red, 50% green, and 30% blue. Okay, and there are colours that you can have like that, but they're imaginary colours. They're colours. We're going to tell you how to see those colours. So you've lived your entire life, and there are colours that I'm going to tell you about by the end of this podcast, which I'll tell you how to see. So how do you do this? How do you see a colour which doesn't exist in nature? What you do is you look at a colour and you preferentially burn out a particular cell. So if you keep on looking at a colour, that colour will eventually reduce its responsiveness. It's because it's nerve cells, so you can actually play with things and actually look at a colour and then look away from it and see new colours that you've never ever seen before in nature. It's pretty, this is why it's so exciting, this type of stuff, to get into colours. Okay, so we've got all sorts of, if I take a sort of picture, what I can do is for every pixel I can say not how bright it is, but what is the ratio of the colours that have gone into it. And if I do that, what will happen is that I will have a surface, and it's a funny sort of surface. So as you go from red, extreme red, you'll only get the red ones, but as that builds up, you'll get some of the green going, and that'll start off flat at a low Z, and then eventually it will curve this beautiful curve. It's sort of like a bent leaf, will bend upwards and reach its highest in the blue, and then it will drop down again. This is it's quite hard to describe for it here. So what we do is we say, well, look, what we're going to do is that we're going to cut it and say that any point, we're going to get a two-dimensional graph, and we're going to have it have a space which is mapped out. The x value of the points that we're going to colour in will be the amount in the red cell, red cone. The y will be in the y cell, and if it's now this is a little bit hard to do because I don't think it's a linear. I think it's the actual, because it's a three-dimensional distance. I really wonder whether you just add the two. I'll just do the add one. I won't do the vector square one. Make it simple for you. So I will make it simple. So if I at the if I have a point where there's it's a little bit more complicated than this. If I have a point at the point of it's perceived. There's a few things in here, but say if I have a point at 6 and 6, okay, that's going to add up to 12. But if you do the power of it, you can. If there's a point at 6 and 6, and the maximum that the green can go is say it's 10, and the maximum red can go 10. There's a missing 4 and 4 from each, so you can actually go through and compute the amount of blue there must be. So any point on the so you have this graph, and you really have to see it. I might post it up there. You have a chromacity graph. Any point on the rim of that graph, that area that you colour in, there is no blue. But any point inside that rim, there is some blue. Blue being stimulated, and you can get different colours by them. So what happens is that you have a curve, and it's quite an interesting curve. So it actually, say for the red, starts, so the red maximum starts at when it's the longest wavelength light, and then it decreases as you go to the green, and this is the trick that humans have got. We've got another lump of visibility in the blue, so it actually increases again. So it never, or it goes from minimum red, the x value goes to minimum red around green, or a bit beyond green, and then it hooks up again. So what we've done is humans have got pseudo 4-color vision. How we've done it is that if you imagine the spectra of the red cone is actually a double spectral cone. It's actually got some sensitivity out in the blue, the extreme ultraviolet. So what happens is that we see something which is bluer than blue. We can tell that it's bluer than blue because our eye starts to add in a bit of red. So this is why when I see something great violet, which is above blue, I can actually make that by getting some normal blue and adding red in my painter's palette, because that's what happens in your eye. Your eye is seeing that extreme blue, and it's actually saying add a bit more red in it. And so there's a sophisticated double set of colours. So that's how that's managed in the graph is that green is fairly simple. So green, there's a maximum wavelength of green, so it goes up to a maximum and goes down. This is mapped against the red, but you see a map against of red response versus, or green response versus red response. And what happens is you get this curve, and it starts off from the right, goes up to the top, goes down, hits the 0 red, and then hooks up again. And so you have this pattern. I wish I could give you a something which looks like a sail travelling to the left. So you can imagine one of those classic sailboat with the triangular thing and the spinnaker, but it's travelling off to the left. So it goes up, the vertical edge of the sail goes over the top, and the spinnaker just touches 0 and comes back again. and inside it we can calculate the amount of blue, and then we put those two numbers, we've got the X, Y, and we calculate what the Z must be and put them as a colour, and so we get a beautiful thing called chromatic graph. And I'll put it on the podcast for you to look at. It's a beautiful thing to look at. So there's the real world, which is much more complicated, but as far as the humans are concerned, we just see in this three-dimensional graph, and we can actually squash it down by restricting one dimension such that we can, from inside that curve, which is a maximum of, so on the edge of that curve there's no blue, but as you come in from that curve in any direction you get a bit of blue. And it's a beautiful thing. So you get sort of a red on the right, green at the top, purple or blue, and then purple again. It comes in. It's sort of like a colour wheel in this Spinnaker sail type of stuff. Now, I must admit I am improving. I'm beginning to actually think and do it in the stress of the classroom. I don't know how I'm going to do this. But in this Spinnaker sail, you've got the intense colours on the outside, and the colours blend into the centre, and in the very centre you see white. That's what humans have been programmed to see, and we can actually print this up. And so that's a chromatic graph. So it's looking at this three-dimensional shape from the top, squishing it down, and then telling us the vertical information in terms of actual colour. We've encoded. It's a two-dimensional graph, but with three-dimensional information in it, because the points are coloured. And so this is a graph. I'll put it up there. Now, there's a few things that when you see this graph and you think about your life experiences, there's two lines of this graph. Now, the one which is perhaps easiest to understand is the very edge perimeter of this graph. So this perimeter of graph has certain colours, and those colours, to me, are very special colours. They're the colours that you get out of a spectroscope. So if you have a line, if you have a spectroscope, a prism, or a rainbow, they're the rainbow colours. The rainbow colours are this line which goes on the very outside of your chromicity graph. And also, a laser beam, a laser source, has to be associated with those lines. And of course, you can get dye lasers which aren't working properly, and you can see things which are obviously not. It's bright, it's got some stimulated emission at broad, multicolored broad wavelength lasers, molecular lasers, and they look different. So as a laser physicist in the darkness of the lab, you get very used to seeing a line, a spectral line, and you know that the spectral lines are machine driven. Now what happens is that I've got a complex colour which I perceive, and what a spectrograph does is push that colour out in a complex way to that perimeter edge, and you look on that. So that's a beautiful thing to see. And so when I'm doing artwork, I like to choose either, I really like hugging to the outside of that line for my colour palette. And it produces dorky paintings, which to me speak a lot, but to other people that's this rubbish. You're not using your colours properly. And again, I'll just talk a bit more about the artistic stuff. But also, there's another little line, which is like a little an eyelash, a curled eyelash. I think that's the way it starts off from the right, the very right point of your triangular sail, and goes up almost directly from the red towards white, and then hooks down gently into the violet. And that's the colour spectrum of all the stars. So all the stars in the sky, if you could pick them up with a pair of tweezers and put them on this diagram, they would form along that line, because that is black body radiation line. There's a black body radiation line. Black body radiation is defined, and the interesting thing is in that line there are certain colours there can't be any green stars. The blue stars are a particular whitishness. It's, you can't get a blue, a blue star as blue as, say, a police siren or something like that. There's a certain combination of stars, and when you look at that, you say that's the palette of stars. So if you were producing a star map, a fake star map, to make it super realistic, you would program that curve in it. So you'd randomly pick an X and Y, a red and a green, and then from that red and green, you pick a red, and you pick an amount of red and go up till you hit the green, that line, which will just tell you the amount of green available, and from that green, that line is pre-programmed to tell you the amount of blue. I won't go into it. It might be a bit confusing there. So this chromograph, I have to think of the word of it. I've only read it. This chromatic graph picture tells you so much to look at it. So you've got the edge, all colours that you can see. Now, it is possible to actually move outside a colour that you can see. So if you can burn your red vision off, look at something red, you can see things. That boundary also limits the amount of colour that you can see. You can see colours which you normally can't make up. And I'm going to put a link to a picture there. This is the burning in colours. So what happens is it's almost impossible to get outside a ratio of red and green, but you can actually there's things where you're actually stuck in there. But what you can do is you can burn out one cell, reduce your colour vision in one area, and then come back, and you'll perceive something different, a colour that you normally don't see. And I'll go into it. Yeah, that's there, and you can see colour standards and the different. I think Adobe, different graphics programs produce different things, and different companies claim so many million colours of photographs, and the depth of TV screens is very much the way you perceive things, especially the actual blackness between pixels. So you pick up your room colour if you don't have a perfectly black TV screen. And the 3 colour LED. So if you actually get a magnifying glass and look really close, or a microscope and look really close at your TV screen or your computer screen, you'll see these 3 colour little pixels coming up, and those 3 colours are just for you to see. Now, the interesting thing is that can be that dogs and other animals, or it's okay for colourblind people, but you can imagine other animals that picture being just a really poor cartoon picture of the actual real thing that they see. So ducks, for instance, see things at a higher grade of reality. So that's chromography, chromatic graphs, will be put in there. And just to recap, we've got light source, which puts the spectrum onto a object, which therefore also modifies the light source, and then that goes into our eyes, and we see it in 3 bins, and we compute it in a fairly complex way, and to produce lights. So we see how much those 3 cones will see. I suppose the interesting thing is that purple is where we sneakily say, oh, blue's not really good enough, I've got to tell how blue it is, so the eye beautifully has a little bit of red in there, so it sees purple twice. There's 2 ways you can see purple. You can see it as a mixture of colours, or as a more pure colour, a more pure red. So you can actually mix the blue and red together by getting a middle of the road blue and a middle of the road red, mix them together, or you can have an extreme violet, which actually does the same thing, but actually mixes it up there. So there's a redundancy, or ambiguity about purple. So there are all these beautiful things. And knowing about this, and you know about the various chemicals that the painters want to or don't have these beautiful toners. They didn't have beautiful computers. They wanted to get certain colours, and without colours in their palette, without certain chemicals, they could only paint certain things. So eventually you can see through art being able to access more colours and more subtlety, and it's a beautiful interplay between art and chemistry coming forward. Art, chemistry and physiology. Thanks for listening. Another podcast, another story comes to a close. It's been a pleasure sharing this moment in time with you. May you discover truly amazing things, understand them and tell others. Thanks for listening.